All right, so at the top of the page here, I have written down the exact same example that I did in the previous video. All right, so we're going to prove the same thing again. Pretend that we didn't already do the previous proof. We're going to prove it from scratch. But this time we're going to use the other strategy, the contrapositive. So instead of assuming P and deducing Q, as a reminder, this is our P, this is our Q. Instead of that, we're going to start by assuming not Q and trying to deduce not P, and then that will be that'll serve to to prove the statement as well. So we're going to begin this one with a suppose. And by the way, I said assume, and then this time I wrote suppose. Those words are pretty much interchangeable with each other, so either one is fine. I'm going to write suppose 5n plus 3 is, instead of even, I'm going to say is not even. It's not even. All right, well, 5n plus 3 is an integer. Okay, we established that in the last video, that integers are closed under addition and multiplication. So I can say 5n plus 3 is an element of the integers. And one thing we know about integers is that every integer is even or odd, but not both. Actually, that's an exclusive or, right? Every integer is either even or odd. In other words, even and odd are, even integers and odd integers are two sets that it's called, they partition the set of integers, right? It's like everything falls into one of those two sets, but there's no overlap between them at all. So I'm going to write, since 5n plus 3 is an integer, and for all m in Z, for all integers m, and I'm just using a different letter because I just need to talk about a generic integer for a moment. For all integers m, n is even, XOR, I could write, exclusive or, n is odd. Since these two facts are the case, if we know that 5n plus 3 is not even, then we can conclude 5n plus 3 is odd. All right, you may have said 5n plus 3 is odd right away, but I want to caution you to not necessarily jump to conclusions like that. For example, if instead of working in the domain of integers, we were working in the domain of real numbers, then saying that a real number is not even doesn't necessarily mean that it's odd, because even and odd are terms that only apply to integers. So if a real number is not an even integer, well, it might be an odd integer, or it might be not an integer at all, like a fraction, or like an irrational number, for example. So just a word of caution there. Be careful not to jump to too many assumptions. All right, so now that we know 5n plus 3 is odd, we can use the definition of odd. I'm going to write then 5n plus 3 is equal to 2k plus 1 for some integer k, right? That's the definition of being an odd number. All right, so now I think what I want to do is a little bit of algebra. I'm going to move things around here. What do I want to do here? I think what I want to do is solve for n, because I'm interested in the properties of n, right? I want to be able to prove that n is what? This is contrapositive. I'm starting with not q, so my goal is to conclude not p, right? And same argument here about everything is either odd or even in integers. Basically, I want to be able to show that n is an even number. So let's try to solve this for n. So I'm going to get, let's see, 5n is going to be 2k minus 2, if I subtract 3 from both sides, which is 2 times k minus 1. I'll factor a 2 out of there. So that's interesting. So 5n is an even number. 5 is an even number. That's pretty useful. Let's put that down. 5n is even. Okay, because we wrote it as 2 times another integer. By the way, in the previous video, in the previous proof, I said like k minus 1 is an integer because the integers are closed under addition, and subtraction is addition. Subtraction is just an addition of an odd number, a negative number, which could still be an integer. I didn't write that this time because I've already explained why that's the case. We can kind of take that for granted now. We know that integers are closed under addition and multiplication. So I'm not going to include that particular line in this proof. So therefore 5n is even, all right? And now I'm going to write 5n equals 2l for some integer l. Now, why didn't I write 2k? Because the definition said k, right? If n is even, then it's 2 times k for some integer k. Well, I didn't use k because I'd already used k for something else, right? Back here when I was saying that 5n plus 3 is odd, I used a k that time. I don't want to use k again because if I use k for 2 different numbers in the same proof, that could just get confusing. And one of the things you want to do with your proofs is you want to make it readable and understandable to me, mainly because I have to grade them. But also, in the future, if you become a mathematician or if you're writing papers, even as a computer scientist, you want your work to be readable and understandable to other people, right? So I used a different letter because it's a different number. And I just used L because it's another convenient letter to use. So 2 times L is 5n. It's odd. It's even. All right, I think what I want to write here next, I'm following my notes here. I thought about this earlier. I think the best way I want to do this is say, well, then I can write L is 5n over 2. Okay, and L is an integer, right? Remember that. So 5n over 2 is an integer. So what this means is that, and I'm gonna kind of dig into some stuff we haven't really talked that much about yet because this proof is a little harder than the previous one. Here, I need to say something about how one of these two, somehow this number 5n has to be divisible by 2, right? And I'm going to have to kind of grapple with this idea that integers are, can be written as a product of prime factors. And 5 happens to be a prime number that's also odd. Okay, so I'm going to write, since 5 is prime and also odd, it is not divisible by 2. But 5n is divisible by 2, so what we actually have to conclude is that, therefore, n must be divisible by 2. So n equals 2 times some number. Let's say n equals 2 times p, for some integer p. So n is even. And therefore, if n is even, n is not odd. So what did we do? We started with 5n plus 3 is not even, that's our not q. And we arrived eventually at n is not odd, which is our not p. And so that is a proof by contraposition. Sometimes sometimes you'll see a line at the end of a proof like this. This is a type of proof called indirect. There's lots of different types of indirect proofs, but anything that's not a direct proof is an indirect proof. And since indirect proofs are a little bit removed from the original statement, often at the end of an indirect proof you'll see a rephrasing of the original statement. So I'm going to finish this off just by saying, thus, if n is odd, right? If n is odd, right, instead of not odd, if it is odd, then the original must have been false, then 5n plus 3 is even. All right, so that's rephrasing the original P implies Q, just as a way to sum up the proof and remind the reader, remember, this is the thing we were really trying to prove, and now we've done it.